All right. Hi, everyone. Good evening. This is Sri Chandra. Thanks for joining in on a Friday evening. So, the topic for today is positive unlabeled learning. We'll kind of do foundations and applications as part of this session. So, let's get started, guys. I think I'll share my screen. All right, we can get started. So, as I was talking a bit before, like positive unlabeled learning, foundations and applications are something that we're going to look into this session. So, a quick about me kind of a thing. I am from Chirala, Andhra Pradesh. I did my dual degree from IIT Kharagpur. My master's specialization was in agricultural systems and management. Soon after I graduated, I kind of worked with Axis Bank's business intelligence unit as a data scientist for close to 2 years, and then I moved to Cropin AI Labs as an AI scientist. So before we deep dive into this session, right, like I just wanted to set up the agenda for this session. We have this agenda very clear. I really wanted to have hands-on included in this session as part of positive unlabeled learning. So we will look into like a quick brush up on machine learning, and then we'll get to look into what is positive unlabeled learning, different approaches or techniques to positive unlabeled learning. We'll do a hands-on of all these techniques that we'll discuss in a short time, and then we'll get to discuss on some real-world applications, and there will be a brief question and answer session towards the end. So we'll try to keep it as interactive as possible. You could keep sending messages in the chat or like on question and answer forum. I'll try to answer as much as I can. So, we could get into like the first part of it, machine learning, like a quick brush up. So, as people who are into data science, machine learning, as people who are data science enthusiasts, we know that machine learning can be kind of uh, classified into supervised learning, unsupervised learning, semi-supervised learning, and representation learning as well. But we'll keep representation learning out of scope for today. We will be discussing about what are like different things in supervised learning. As you can see on the left, there is classification, regression as part of supervised learning. There is clustering as part of unsupervised learning, as an example. And as part of semi-supervised learning, there is text classification. We could consider text classification as a semi-supervised learning thing. So what do we mean by supervised learning, semi-supervised learning, and unsupervised learning is given on the right. What is the technique and what is the kind of training data that is there as part of these learning techniques. So supervised learning, when we say supervised learning, it's the training data will have like labeled data sets available with it. Semi-supervised learning, there's a mix of labeled data set and unlabeled data set. And unsupervised learning is more like you do not have any like labeling available with you. So just a quick checkup, right? Like, what do you think like positive unlabeled learning will fit into these three learning techniques? Where do you think it will fit? Right, like can you maybe put it in the chat for me to see like the understanding of it? Can the answers keep coming like the chat? I can see there are no answers as yet. Right, unsupervised, semi-supervised, some are saying unsupervised, unlabeled learning maybe. Many are saying it's unsupervised learning. We'll see like what it will fit into, right? So positive unlabeled learning, it's kind of a variant of semi-supervised learning, and we could get to see like the difference between semi-supervised learning and a positive unlabeled learning kind of a setup, right? Like supervised learning, if you see on the figure, you see that there are positive and negative data available with you for training. And as part of semi-supervised learning, there's a certain portion of positive samples, there's a certain portion of negative samples, and there's some portion of unlabeled data available. So positive unlabeled learning, if you're looking into it, positive samples are available, like the positive instances are available. The rest of the data is all unlabeled, right? It's a different setup, right? Like when you look into these kind of problems, you definitely do not have a kind of a framework where you would solve this as a classification problem, right? You definitely know that there are some positive instances, and what if there is unlabeled instances with you, and how do you deal with this kind of a problem, right? Classification, when we do, we at least have heard about binary classification, multi-class classification, and all of that. So when we consider binary classification, it's more like there's a certain portion of positive instances, and there is certain portion of negative instances labeled with it. So this is what it makes PU learning different, right? Like the PU learning is a kind of available to deal with this kind of unique scenarios, and we'll look into how there's literature around PU learning for us to deal with this kind of problems. So as part of PU learning techniques, like when you think about this problem, when you know that there is certain amount of positive instances and there's nothing available as part of negative instances, the first thing that maybe comes to your mind, as it came to my mind as well, is something like, why don't we consider this as a problem of standard classification, right? Like, why don't we consider positive instances as positive instances, and the unlabeled instances as negative instances with a lot of noise? So that is the first kind of approach or a technique that's followed in the literature. That is, just treat the unlabeled data as highly noisy negative data, right? Like this is the first approach that comes to our mind when it comes to positive unlabeled learning kind of problems. So the next thing is more like saying bagging kind of an approach, where you'll say like, hey, we have some positive instances with us and there's some amount of unlabeled instances. From the unlabeled instances, we'll take equivalent portion of the data, kind of do classification and get the positive instances out of the unlabeled instances which are predicted, and then use the same data, iteratively bootstrap the data and get the classification. So that is one approach, right? Like the bagging is more like doing random forest, suppose say. You can consider that. We are saying as part of this technique, create a bootstrap data set and apply the standard classifier to these out of bag samples to finally arrive at estimated probability of unlabeled samples to be positive, right? Like you could come up with a probability saying that this probability above which, if there are any instances, we'll be considering them as positive. The third approach is a two-step strategy, where we are saying, hey, as part of the unlabeled instances, suppose say there's a scenario where you definitely know that there are reliable negatives in that unlabeled instances set, right? Like positive instances, you definitely know like this is a positive sample, and as part of unlabeled instances, when you look at a certain portion of the data, you may be arriving at a situation where you know like this is definitely not positive, and we could consider them as reliable negatives, and we'll identify such reliable negative examples in the unlabeled data set, and then use kind of a binary classification on top of it as part of the first step. And as part of the second step, we could iteratively do this supervised learning binary classification thing and come up with new positive instances that are getting predicted and new negative instances that are getting predicted across some fixed estimators. So we have discussed mostly the popular techniques around PU learning, and the next one is more like an ensemble, right? It's more like an average of these three approaches, and we'll kind of get to see like how these three are performing in relation to the average, correct? So these are essentially the four approaches that we are going to deep dive now. So we'll just have like a hands-on session after this. So average, as I said, it's a sort of fourth approach to compare to the rest, where we say like we calculate the average score, like the probabilities of all these three techniques. We'll average them and we'll use the probability threshold to kind of classify it to positive and negative instances. So we have like a collab notebook. I'll quickly share that. I was on mute. I was talking, but then I'll kind of uh, rediscuss on these things. What I was trying to say was we will spend a lot of time digging into this notebook. Each of the cell will go through the data set, will go through and will go through each of the approaches, each of the three approaches that we have kind of discussed previously in the slides. We'll see how each of them are performing, and we'll kind of look into how we could extend this same three approaches to your own problems, and we'll see what is possible and what is not possible as part of this approach. So we'll get started. I think we'll read the packages, right? And we are using a synthetic data set as part of this presentation. So what we're looking at is 5,000 samples, which are like spread across in a Euclidean space into four clusters. So I'll just run this cell, and once they are into four different clusters, we are kind of converting the original labels 0, 1, 2, 3 to 0 and 1, and which means 1 is a positive instance and 0 is the unlabeled like kind of negative instances at this point. We'll look into how many data points are there, right? Like 5,000 data points are there, and there are two features, and out of the 5,000 data points, 2,500 are positive instances. So this cell, what we are trying to do is we are preserving the class distribution as per the original data set. We are trying to unlabel certain samples of these positive instances and have only a minor portion of these instances for training available, right? So what I'm trying to do is, out of these 2,500 positives, I am kind of unlabeling 2,000 instances here as unlabeled, right? And okay, so we could try maybe 1,500, like 500, right? So we're trying to do unlabeling of 500 instances, and we'll see like how this will go, right? We'll kind of come back to how this will perform. Just a second, there's something wrong. So, right, as I was explaining, there are 2,500 positives out of 5,000 samples, and we have kind of unlabeled 2,000 of them. And we have 500 positives out of 5,000 as part of our new data set. We're just looking into how the data set would look like in the Euclidean space, right? You could see that the crosses that are there, they are unlabeled instances. Out of them, all 5,000, we have like 500 instances which are positive at this point, like the new data set that we have. So we'll dig into like the first approach, which is more like a standard classifier model, right? Like we'll consider positives as positives and unlabeled instances as negative instances, which are highly noisy. So by noise, what we mean is like with along with negative instances, there will be positive instances as well, which would be considered as noise for the model. we using random forest classifier for this approach. We'll look into, like, we're just doing the normal, right? Like we define the classifier, we're fitting it, and then we're trying to get the probabilities out of it becoming a positive. So we'll just run this, right? And this is run, and we get to see how it's performing on the data set, right? Like you could see this on the right side is a legend where it's from 0 to 0.35, the probabilities are varying, and you could see the original distribution. Say you have like the diagonal clusters as unlabeled instances which are actually negative, and like there is red points which are positive instances, and all remaining ones in these two clusters are unlabeled ones. So you could see for the standard classifier model outputs, you could see like the red color points are the ones which are having like close to 0.25, lesser than 0.15 to 0.25 kind of probabilities here. And we could actually kind of decide on a probability threshold for us to, identify the positives in these two clusters. So this is one approach that could be possible as part of the positive unlabeled learning. You could decide on the threshold, and this can be taken up, and accordingly we could say like some which instances are greater than this threshold, they'll be considered as positive, and the other instances which are falling beyond this probability, they'll be considered as negative instances. So the second approach is like the bagging approach. We'll spend a little more time on this one. We'll try to understand like what will be done in this approach step by step, and we'll create the we'll run the cell and we'll look at the results, right? So the bagging model, which the first step that it's done is we create a training set by combining all the positive data points that we have with a random sample from the unlabeled points with replacement, right? Like it's bootstrapping basically. So what we're trying to do is, if you look at the original data set, what we have is like a 5,000 instances where 2,500 are positive and 2,500 are unlabeled instances. And out of these 2,500 positives, what we have done is 2,000 we have unlabeled them as unlabeled instances, and only 500 out of these 2,500 are being considered for the model training. So you could see, like when we are saying creating a training set by combining all positive data points, what we have is like a 500 instances set. With that, we could combine 500 instances each from the remaining 4,500 instances and do more like a bootstrapping kind of a sampling, and build the classifier. The next step is we build a classifier from this bootstrap sample, treating positive and unlabeled data points as positives and negatives respectively, as I was discussing. And we apply the classifier to whatever unlabeled data points were not included in this random sample. We will call them as out of bag instances, right? And we'll record their scores, right? By scores we mean like the probabilities, we'll record them. And what we'll do is we'll repeat the three steps above many times, and finally assign to each point the average of the out of bag scores it has received. If you closely look at this approach, it's more like doing what do we say, k-fold cross validation or a stratified k-fold cross validation kind of a thing, where we create like 5 folds of the data set. We kind of train on 4 data sets and test on, like predict on 1 fold. We do that 5 times and we take the average, right? It's similar to the same thing. We could consider this approach as well, similar to the same thing. So what we are essentially doing here is we are kind of using a decision tree classifier. We could use any other estimator as well. For simplicity, I think we could use a decision tree classifier. And what we are here doing is we are kind of getting the indices of positive instances and the indices of negative instances in this line of code. After that, we are just instantiating like the number of out of bag samples and like the sum of out of bag samples kind of a thing. And after that, we are going to use 1,000 estimators. And here is the bootstrap sampling that I was talking about, right? Like we are going to choose randomly with replacement equal to true, and the size is going to be equivalent to like the positive instances. So the positive instances that we have is 500, if you remember, and we are going to get 500 samples randomly from the unlabeled instances, which are 4,500. And with replacement, we are going to use the same indices and get the data set prepared in such a fashion where like the data sets are going to be 500 positive and 500 negative instances for each of the iteration that happens inside the loop. So we're going to fit the same thing on the features and the labels that we have. We kind of converted the labels based on the same logic. So once we did that, we kind of predicted on the remaining instances, like the unlabeled instances, and we're getting the score of it. So once we have like the summation of the probabilities across all the estimators, what we're trying to do is get the average of this thing, and we're kind of storing that probabilities in this results. So I think we did not run this. We'll run this. I guess like I made myself clear on this particular approach. Right, it's running. We'll get to see how it's performing. Right, in terms of the probabilities, we'll get to know how well it's performing. Right, it has run. So the same way as standard classifier model, we get to see the probabilities, correct? If you can kind of look into this plot, you see that the range of probabilities did not go above 0.35. So if you're looking at the bagging approach, the PU bagging approach, you see that the probabilities are ranging from 0 to 0.8 and even beyond, right? Dark green patches, they could be beyond. And you see that there are some instances which are red. There are some instances which are like violet, some are blue. You could see there are instances which are red and all of that. So you could see like the data, according to the data, the approach is seemingly doing well. So we'll kind of have these results stored in a different thing, and we'll move to the next approach. So this is the two-step strategy approach that I was talking about, right? Like when we talked about positive unlabeled learning, we said we have positive instances, right? And we have like unlabeled instances. And if there is a possibility, if you could identify reliable negatives as part of your use case, you would be able to consider them as negatives, and you could create a model as part of first step as a standard classification model, and use the positive and negative data points to train a standard classifier and apply it to remaining unlabeled points. We'll go through them one by one. We'll understand the code and we'll run it. So this is the two-step strategy model that we're trying to achieve here. We identify a subset of unlabeled data points that can be confidently labeled as negatives, and we call them like the reliable negatives as part of the references that I've done and the research that has happened. The authors of the paper above call these points as reliable negatives, right? So what we're trying to do in the first line of code in this cell is trying to create a new target vector with 1 for positive, -1 for unlabeled, and 0 for reliable negatives. So as part of our data, we do not really have something as reliable negatives, right? So it's 0 for us. So there are no reliable negatives to start with. So what we're trying to do is a new target vector, which is ys. It's 2 times y minus 1. If you're looking at 2 times 1 minus 1, it's 1. If it's 2 times 0 minus 1, it's minus 1, right? So you have like positive and unlabeled, and 0 will be reliable negatives. So the random forest classifier that we kind of trained here, like the fitting of this has happened here. So we're using the same thing to predict on the data set, and we are kind of looking at the range of range of probabilities given to positive data points. As part of step one, what we are trying to do is, if any unlabeled point has a probability above all known positives or below all known positives, we'll kind of label it accordingly, right? Like we're trying to get new indices now. What we are trying to say is the new target vector that we've created, if the value is less than 0, and like the prediction is greater than the range, right? Like the range is min and max. If it's greater than the positive data point probability, positive data point probability, you will assign it to the new positive index. Otherwise, you're going to assign it as a negative index, and you will kind of impute the values of the target vector as 1 and 0, and you get to see like how the results are as part of step one, right? Like as part of step one, how is it looking? And as part of step two, what we're trying to do is we're going to use that same random forest classifier, and because it will take much time, right? Like we wanted to limit this to 10 iterations. You could definitely increase it to 100,000, whatever works for you. But as for demonstration, we I kind of use 10 iterations. So in these 10 iterations, what happens is, if the step one didn't find any new labels, we're done, right? Like we do not need to do anything. If the step one has found out like new positives are like new negatives, we'll kind of do this iterative approach of retraining new labels and get new scores, right? Like what we're trying to do is say, in the first step, we kind of got like 25 new negatives labeled. We kind of use those 25 negatives as part of the standard classifier, and kind of use the model training on it and get the probabilities, and also get a range of scores that will be like given to the positive data instances. And again, like the step one will be repeated, right? Like when the value is less than 0, and like the prediction probability is greater than the positive instance maximum, we kind of create like the new target vector again, re-impute it, and the resultant probability, right, like the predictions will be stored in this two-step results in this one. So we'll run this. It will take a little bit of time, but we'll get to see like how the results are coming. So as part of this, you could see, right? You could see that these red points are all unlabeled, and as part of the first step, you saw that there are 0 new positives, but there are 2,420 new negatives, right? So we iteratively do the step 2, and we kind of look into how many new negatives are being considered every step, and that will do for 10 iterations, and that will be the end of it. So we'll just see like how this approach is performing. So you see, it's more similar to the standard classifier, right? You see that the both the things are classified as like 0, and in these two clusters, there are data points where the probabilities are lying in the range of like say 0.15 to 0.25. So we have looked into like 3 approaches now, and these 3 approaches will have to see like how they're actually performing in terms of number of proportions, like the proportion of positive data in the unlabeled instances. So as part of the fourth approach, what we discussed about is like taking an average. So this does it, right? Like the average is basically the standard classifier, bagging, and like the two-step approach. We just take like the mean and then we get the data. We could see like how this is performing with the average of these models, and you see like the probabilities are close to like zero point 0.5, like the maximum probabilities are coming down to like zero point 0.5, which is better than like the standard classifier or like the two-step approach, right? Before we go look into the performance graphs, I just wanted to reiterate like the three approaches so that like there is clarity. We'll do from step by step from the beginning. We'll just understand the summary part of it. So what we have done in this hands-on session is we've created a synthetic data set, which is four clusters, like four centers. They are there, and there around the centers the blobs are created, and like there are 5,000 instances as part of our data, and we have converted the original labels 0 1 2 3 to 0 and 1. You have like two features. You're creating a pandas data frame, and you have like the y as a pandas series format, and you have like 5,000 data points as part of the data set, and there are two features. Out of these 5,000 data points, there are 2,500 positives. And what we have done for the purpose of this study is we have unlabeled 2,000 of these 2,500 positives as unlabeled data, and we only have like 500 positives which are used for the model training. We have looked into the data, like we have seen like all negative instances, like the unlabeled instances are cross marked, and like there are 500 positive instances distributed across. So you have like the standard classifier model. As part of the first approach, we have used random forest classifier, and we have trained it with the original data set, and we have kind of looked into probability scores, and we saw like how each of the point in our data set is performing, right? Like the probabilities, how are they looking in this graph. We saw that the probabilities are not even like going above zero point 0.5, which is the usual case, right? When we do binary classification, what we do is the values which are greater than zero point 0.5, we classify them as positive, and which are less than zero point 0.5, we classify them as negative. At this point, maybe like if we are considering a probability threshold of say zero point 0.2, we will be able to get some positive instances from this approach. So the second approach is like the bagging model, where we are saying, hey, we have like positive instances, we have like unlabeled instances. Out of the unlabeled instances, we'll take a random sample of like say 500 instances equivalent to the positive instances number. We'll create a model on this positive and negative like unlabeled instances, get the probability scores, and we kind of do this iteratively, more like doing a cross validation. And after we do this repetitive procedure, we kind of get the average probability scores with this approach, and we have seen like how these probabilities are looking like on a 2D space. You see like the probabilities are actually diverse, right? Like they're varying a lot from 0 till like 1. You see like there are larger portions of 1. You if We could get to this later as well, but these portions are actually, if you see, are like the positive instances, right? Like these are the ones that we have considered as positive instances, but we have knowingly hidden them just for the purpose of this demonstration. So the third approach that we've looked into is two-step, where we say, okay, out of these unlabeled instances, I can classify some instances as reliable negatives, and based on that, in the first step, we kind of get the probability set up, and in the second step, we kind of iteratively do the classification, get new positives and new negatives, and like they club it with the positive negative instances, and kind of get the final probabilities assigned, and we store them. So and the next thing, right, so this 2D space is looking like this for two-step strategy. And again, just like how we have discussed about standard classifier, maybe a 0.2 or a 0.25 probability. If we kind of use it as a threshold, we might be able to classify positive instances properly. So that is there, and like the average approach is very simple to understand. So this is the summary. We have seen, like for average also, it pretty much varies, and there's a lot of subjectivity to this problem. So we're finally trying to look at how this is going to work, right? Like we are going to look at the performance. We are going to prepare the data. How are we preparing is we're looking into samples. Like we are kind of splitting them into 100 each, and like we could see how they are performing on a chart, right? Like on a plot. So this is the plot that we are looking to, kind of understand all the four approaches. So here it is, and I think I'll just minimize a bit. Right. So if you're looking at this particular chart, right, like what we have as part of x-axis is the number of unlabeled data points chosen, and the percentage of chosen samples that are hidden positive, right? Like what we have initially considered is 5,000 samples, and out of these 5,000 samples we have like 2,500 positives and 2,500 negatives, and like out of these 2,500 positives as well, we have considered 500 positives for the purpose of the study, and like 2,000 are secretly considered as unlabeled. And across this we could see like how each of our model is performing, right? Like each of our approach is performing. So if you see, standard classifier is a blue colored plot, blue colored line. PU bagging is orange. Two-step strategy, it's green. Average is the brown or the red color that you're seeing on the plot. So if you see the proportion of like the number of unlabeled data points by if the number of unlabeled data points are increasing, the performance of like the standard classifier and the two-step approach has come down, right? Like drastically. If you see, after say 1300 or like 1400 unlabeled data points, we see that the performance has come down. With PU bagging and like average approaches, you could see it's pretty much generalized, right? Like across a proportion of unlabeled data instances, you see that we are able to achieve a better results. And like the average is also keeping up with the bagging, right? So mostly we can consider average is going in line with bagging approach, because like the probabilities are also suggesting that bagging has a lot of higher probabilities that were given out of this scope, right? So this is all hands-on about these three approaches that we have discussed. And just wanted to like uh, pause here, try and understand, right, how they're doing, and we have discussed that as well. So this is all about the hands-on session, and I think we could get back to our slides at this point. This is all that I had, and I'll get back to the slides now. I'm stopping the sharing. I'll share these slides now again. At this point, I'm just looking for any questions. Okay, somebody was asking link to collab notebook. Definitely, I think notebook and slides will be shared with the data team, and they'll kind of put it out in the YouTube description. I'll kind of ask them to do that, or otherwise you could reach out to me on LinkedIn or on my email ID. I'll be happy to share. So I'll just share my screen for the slides. Yes, I have unmuted this time. So After this hands-on peer learning, we could discuss about the real-world applications now, right? Like this is something that's really interesting to me. All the theory and all of that, I think it's really boring, right? Like until we get to know like the real-world applications, right? Like okay, there's PU learning, something like supervised classification. There's something called PU learning, and then you get to do classification. And how does that really make sense to any data scientist, right? Like if it's not applied in the real world. So if you're considering fraud detection as a problem, which is a really big problem in like the banking or like fintech places. So what do you have really as part of fraud detection is, like the team can sit and understand and say like the customers have come and said a particular transaction ID was a fraud, right? Which was done by somebody else and it was not done by the customer himself or herself. So the data can be in a such a fashion where you only have like positive instances with you. For example, when we are talking about fraud detection, we're talking about cases where we have fraud tagged, right? Like all the transactions, we definitely know like the transactions which are tagged as fraud, and there are definitely going to be many transactions in the transaction databases which have gone unnoticed as fraud, and we do not really have like pinch of a hint there, right? We don't really understand whether a particular transaction is fraud or not. So for fraud detection, I really think positive unlabeled learning is really relevant. I think many people across industry and across academia, I think for fraud detection, positive unlabeled learning is used. So that's a really good use case, right? Like fraud detection is one particular area where you could use this. If at all you have to solve fraud detection without using PU learning, you'll have to do the standard classifier approach that I was talking about, correct? Like the standard classifier saying, hey, we have like positive instances which are fraud, and we have like unlabeled instances which we will consider them as negative, and definitely in that negative instances there are going to be samples which are positive, and they are going to be noisy, and like the fraud detection models may not be performing well in terms of the evaluation metrics and all of that. So one area that I see like fraud detection is really applicable, like the positive unlabeled learning is really relevant, is fraud detection. Second is text classification, right? Like if you have to do text classification, say you're trying to tag documents, or like say tag Twitter tweets as political, or like say sports related, or like say cinema related. You cannot sit and tag everything, correct? Like you cannot always sit and label every tweet as political tweet, every tweet as sports tweet, and all of that. So there you have like ample opportunity to use positive unlabeled learning, right? Like when you have like instances, say a multi-class problem also, like the positive unlabeled learning can be extended. Here we say like there are 500 of tweets, we will tag them as political, 500 tweets is sports, 500 tweets is cinema, and all other we'll consider them as unlabeled, and maybe say we'll use them as like as part of positive unlabeled learning. Maybe we'll use a two-step strategy to iteratively predict the unlabeled tweets as political or sports or like cinema. So that is also a relevant use case where I can see positive unlabeled learning is of much significance. Another thing is the wearable sensors, right? Like the sensors that we wear, like the watches, with the Apple Watch. You see, you definitely must have seen that there are news around Apple Watch saving lives and all of that. Thanks to technology, we are really progressing it that way. I think like with sensors as well, right? Like when we track, when we look into the data, it's a streaming data, and when you look at sudden spikes in terms of BP, blood pressure, or like heart rate, all of that, we only have like these sudden spikes, right? Like these sudden spikes can be considered as positive instances, and we do not really know like the slightest of a spike which we do not get to have an alert or something. They can be of use, right? Like they can be of significance to understand any early kind of a heart attack or something. So wearable sensors is another area where I see like positive unlabeled learning is of significance. Again, with novel disease detection, something that is new, right? Like something with COVID-19, right? Like with coronavirus, we were not sure like how do we test it and how many like positives, negatives are coming, all of that. So for a new disease where like the sample size of the real examples or like the instances for training are less, there we could use positive unlabeled learning and then iteratively kind of predict on the unlabeled instances and kind of have a threshold to say, hey, you might have a coronavirus or something, and they could take precautions, right? Instead of having false positives or like false negatives, we could actually use positive unlabeled learning and be a bit safe. So that is one area I see as a potential use case for positive unlabeled learning. And as part of one class, crop detection, somebody who is into remote sensing, satellite imagery, one class crop detection. This can be a use case for a positive unlabeled learning, and also wildlife monitoring, right? Like for wildlife monitoring, you definitely will not have like the photographs or images of all the wildlife that's there in the forest, right? You will have like representative samples, and like you'll have to kind of use them only and do classifications or like any other predictive modeling on top of it. So wildlife monitoring is also one area where I could see a potential use case for positive unlabeled learning. And this just doesn't end here, right? Like positive unlabeled learning, just like supervised classification or like same like the clustering, regression, all these problems, it can be applied to any other problem, right? Like you could someday say in banking, I have come across a problem where this can be applied, and you could see how this is performing as part of the evaluation metrics and all of that. So I'm really curious. I really want to know like the knowledge that you've gained from this particular session. How are you going to use, right? Like positive unlabeled learning, you're going to use it elsewhere, and you're going to get good results. If you're getting them, I'll be more than happy. So that's all I had. I think as part of this session, we can have a brief question and answer session as part of this. Also, you can connect with me on LinkedIn, on email. I will be very happy to answer your questions, get connected, and we could explore potential opportunities there as well. So I'm open to questions now. I think we have dwelled into many. I have kept it easy, like I kept it very simple. We have maybe I'll just have a quick summary, like a 3-4 minute summary of the presentation, and then we can have the question and answer session. So what we've looked into is machine learning, like different techniques, like the supervised classification, regression, unsupervised learning, semi-supervised learning. What does it mean? What is it? The differentiating factor as part of labeling, tagging, label data set, and all of that. We have seen like how positive unlabeled learning is different from semi-supervised learning, although it's a variant of semi-supervised learning. We have seen like multiple approaches. There is standard classifier where we treated the unlabeled data as highly noisy negative data. We have seen like a bagging approach. We have seen a two-step approach where there's a possibility of you identifying reliable negatives, and you could use this approach to solve the problem at hand. And you have like a average of all these approaches just for the comparison. You could use it for your own use cases as well, right? And we have seen a demo notebook as well with the synthetic data set that we have used. We kind of demonstrated how these three techniques would work, and we have seen like the comparison among them. And I think positive unlabeled bagging, the bagging approach was doing better. It may not be true all the time, right? Like it depends on the data set. It also depends on how you're using the techniques to your advantage. So definitely, I think every approach is a good place to start with, and you could explore like which ones are working for you, and you could use the approach that's working for you. And I'll be very curious. I'll be very happy to know like if this is helping you. And we have also looked into like the real world applications, some of them, and you could come up with a lot more after this presentation. The whole idea of my presentation was to bring all of you to know about something called positive unlabeled learning, and you could potentially use it for your own use cases across domains, right? I was working in banking and agriculture, maybe somebody who is working in e-commerce, somebody who is working in a different domain could use it and make the best use of this approach. That's all. I think I'm open to questions now. So in the chat, um, all right, guys. I think I am open to questions if you're having any. I will try to answer them. I have like these references maybe. These are the references to positive unlabeled learning, and like somebody who really wants to get into the research side of it, want to understand more about positive unlabeled learning. Here are the resources. I think I'll share my slides and also the notebook with you separately, and you could get to read on all these references, and this will be of help to you. So that's all I had. Like, thank you so much for joining in on Friday evening. I really understand what Friday brings, and I really hope like I had something to share with you all, share the learning with you all, and I am really curious. I'll be really happy to know you have used positive unlabeled learning for something in your own domains, or some use cases in your own domains, and how it has helped you. It will be really great. Thanks, everyone. Thank you so much for joining. That's all I had.